Good day, guys. Darian Giuseppe here, back again with another video for the Key Concept series. In today's video, we are going to look at a worked example on a Module 1 question, a Module 1 past paper question for Pure Maths Unit 2. Right, so this question is based off of integration and more specifically integration by parts. So with that said, let's get into the question. The question says, let each be a function of x. Part 1 is saying, show that the integral of h to the power of n by ln of h with respect to dh is equal to h to the power of n plus 1 on n plus 1 squared multiplied by negative 1 plus n plus 1 by ln of h plus c. And they give us some particulars here where negative 1 is not equal to n, which is an element of the set of integers, and c is an element of the set of real numbers. So anytime I am asked to show anything, I like to write RTS, and I like to write down what it is the question is asking me to show, because you want to always have in mind what it is you're working towards. That is very key. So then I would say showing. And what do they want us to show? They want us to find, well, they want us to show this, we know that, right? Or they want us to show that the integral of this is equal to this. That's what they want us to show. So let's start here with the integral of this here. The integral of h to the power of n by ln h with respect to dh. What you need to, well, the first thing, looking at this question, I am thinking, can I integrate this by recognition? And if you go back to the video that I did on recognition, you would notice that no, you can't, right? And you look back at the tables of the different integrals that you need to learn via recognition, you would notice you can't. So because we notice, or if you take another look, you would notice that this is a function of x and this is a function of x. And because, right, they are asking us to find the integral of the product of two functions of x, we use integration by parts. So once you've identified that, then the next thing is to recall the integration by parts formula. What is it? This is the integration by parts formula here, right? The integral of this here, this entire thing is given by this. So once you recall this, that's really nice. But the next thing now is to make sure you set it up properly, right? And when I say set it up properly, you want to make sure you, and let me just bring this down a little bit. You want to make sure you identify who would be a u and who would be a dv on dh in this part of the integration by parts formula, because that is very important. So that would be a key, right? You want to identify who would be a u and who would be a dv on du. So let's see if we could try to figure that out next. That's what we want to do. So what we could use is actually the Liat rule. Remember the Liat rule that I spoke about in the video I did on integration by parts? Yeah, so we could probably use the Liat rule, right? This little acronym here, which tells us who would be given preference to be our u, right? If we look at the function, we have to look at the function being integrated. Let's look at that. This is an algebraic function. H to the power of n is algebraic. This is a logarithmic function. So what we notice, we're dealing with a log and algebraic. And what the Liat rule says is, right, the higher the function is in the acronym, the functions higher in the acronym would be given preference to bu. So as a result of that, you can see off the bat, we know who gonna be u. Ln of h will be u, and dv on dh would be h to the power of n. So that's basically that. That is the initial setup. You want to make sure you get this correct. Once you get that right, you're on the right track. So u would be ln of h, dv on dh would be h to the power of n. The next thing we do now is differentiate this and integrate this. So differentiating the u, we will get 1 on h. integrating this, we would get v, which is you increase the power by 1 and divided by the new increase. That is what was done here. Now, we have the terms we need to populate this part of the equation this part of the formula for integration by parts. So you can take this here and multiply it by this to get your u by v, and then we can take this and multiply it by this to get this here, and then we could start the work. So this is what we have here, your u by v, that's this by this, and that's how we get this. And the next thing we need to do is multiply this by this, right? And well, don't forget your integration sign and that negative, your integration sign and the negative sign, right? So this is what we have next. And then all we need to do is really just simplify a little bit. I'm seeing we could look at this here and simplify it a little bit. We could take this, you see this n plus 1, we could carry it outside here because n plus 1 is considered a constant in this case. So the n plus 1 could actually come out here. That's a constant. So we could use that rule of integration and just bring him out of the integration sign. So that's what I would do in the next line here. Just simplify a little bit before I start to integrate. So now, let's integrate this. This should be simple integration by recognition here. H to the power of n would just be h to the power of n plus 1 on n plus 1. So this is what you would see here. Increase the power divided by the new increase. And you plus your c, constant of integration, right? So you increase the power divided by the new increase. Notice, I have not done anything to this term on this term has stayed the same right through, right? Just notice that. And the next thing we can do is we can multiply this guy by this guy here so that we could further just simplify a little bit and see where we at in terms of getting what they want us to show. So this here does not really look like this, what they want us to show. But you see this part here kind of similar, so that's cool. And then I see now ln h here. It's looking like a kind of factorization taking place here. So let's try to factorize out the h to the power of n plus 1 on n plus 1 all to be squared, right? So let's go over here and check that out. Let's see what will happen here. So this is what we have, right? What I did here, I just rearranged these two terms. You see these two terms here? I just rearranged them. I put this first and I put this term last. And then factorized it. I factorized out the h plus 1 on n plus 1 all squared. And what you would notice, this is what they want us to show with your constant of integration. Don't forget that. Right? And we can just check it out. This multiplied by this would give us back this here. Right? And then this multiplied by this will give you back this, because the n plus 1 here will multiply by the n plus 1 squared, and it will just give you back this here and multiplied by the ln h. So you're good here. Once you have this here, that's it, and you have solved part 1. You have showed what they asked you to show. So that's part 1. Now let's look at this part 2. They say hence find this here. Interesting. Let's check or try this on another page. So this is part 2. Let's write down what they're asking us to find. This is interesting. They say hence. Whenever they say hence, that should mean you want to use the information in the previous question or the previous part. But this integral here does not look like this. We have to try to bring it in terms of that. That is what we need to do. So to bring this in terms of this, or to make it look like that, so that we could utilize this integral or this result here that we got in part 1, what I'm going to do is I'm going to use a substitution. I'm going to let sine x be equal to u. And I'm going to differentiate it. And I'm going to just manipulate it a bit. What you'll notice is this. If we replace sine x by u, you would get ln of u. If we replace sine squared x with u, you would get u squared. And then if you look at this result here, the cos x and dx, right, if they multiply by each other, they are the same as du. You notice that? So we could replace cos x and dx with du. That's where you will notice these two could be replaced with du. That's really cool. And it may formulate, or what the result we might get should look like this. So let's see what will happen. That's what I'm thinking. Let's see what will happen. Right, let's label these two equations 1 and 2. Right, so there's equation 1 and 2, and we're going to substitute them, right, these two equations into this integral and see if the substitution will work. So when we do it, this is what we will get here. Really nice. And look at it, it looks just like this. It's just the n, instead of n we have 2. Instead of n here we have 2. So wherever we have n in the result that we have here in part 1, we would just replace it by 2. So that's what we could do here. This is really interesting. This is really nice. So we could use the result from part 1. Right? So this is our hence moment. This is where we're using the result from part 1. This is our hence moment. This is beautiful. This is brilliant. And this is what we will get here. All we need to do is just use that result. We do have to integrate again. So this here, we're just going to use this entire result here. Don't forget your plus c. Right? And replace wherever you had n, you're replacing n with 2. So that would give you 3 in most instances. Or in all the instances where you had n, you would get 3, right? So it would have been 2 plus 1, 2 plus 1, 2 plus 1. That's how you get the 3's there. And then, just simplify this a little bit. Square that 3 in the denominator. And it will simplify to this. And this is now your final answer. You have to remember u is equal to sine x. So replace u with sine x throughout, and that will be your final answer. So this was an interesting question here. This is your final answer here. Right? This is your final answer here. That is that. So this, guys, or those two solutions that I just ran through there with the solutions to these two parts here. Pretty interesting question. I hope you guys understood this one. Like the video. Feel free to share it to somebody that you feel it will be helpful to. And with that said, I will see you in the next video.